Excellent. So first, let me introduce Anna Kate Moore, who is serving as our course moderator. If you have any technical issues or needs, uh, I want to just welcome you and basically make this pitch to you, okay, real quick. What we're doing here is gaining a lot of traction very quickly. We started a pilot program last year, everything filled up. We're approaching 500 student fellows now, which is really remarkable. So that's possible because good people like you have a thirst to be united in wonder with something great through great texts and great professors. And the difference between what we're doing and most other online delivery of content methods is that this is live and interactive. So really the difference between these classes and most of what you can find online as far as intellectual formation, the difference is you. And so this works to the extent that you're here, that you're present, that you're in class. If you can show your face, that's great. If you see me with an admin screen blacked out or somebody on our staff, they're just there editing podcasts. So that's really the only time we should have blacked out faces. Other than that, show yourselves. We are recording these for podcasts, for potential YouTube videos down the road. So your interaction will be recorded. Hope you're okay with that. If you do say anything that you want edited out, just let us know. We'll take care of it. But you are, as many of you know from being in the seminar method and growing up that way, right? You are here to be educated as well as to be co-educators, okay? And so this class works through your participation. And with that, if you can support the work of the Albertus Magnus Institute through a monthly donation of any kind, it makes all the difference to the world, in the world. For us, I'm here as a volunteer. Many of the people that got this thing off the ground are completely volunteers. We do have expenses, and that we've been able to do so much with so little to this point has been something of a miracle. But the number one criticism of our approach, and I mean number one, like by far, and this was Seeley's criticism when I pitched it to him. He says, "Why are you doing it for free? Why are you doing it for free? People don't value what they get for free." And what we'd like to do is prove these naysayers wrong. And we're trying to do that by gambling precisely on your generosity. So we're going to deliver the goods. You got the certificate that you can frame, put on a resume, whatever you want. But the rest is learning for learning's sake. And that is possible, especially in these infant stages, with your generosity. So if you can't handle a $10 a month donation to the Albertus Magnus Institute, do me a favor and just shoot me an email and tell me why. Because we've got a Franciscan monk with a vow of poverty giving us $5 a month. We've got multiple very broke college students giving us $5-10 a month. So if you can help, that'd be great. And as a bonus, what I can do is give you for $25 a month. We just opened up recording archives for any other class. So if anybody's giving over $25 a month, you can actually get free access to all the courses that we've done. So if there's another class you kind of were on the fence about, you wanted to take, but you couldn't fit it in the schedule, this is a great way to just be able to watch all those recordings. So help us out if you can, and we'll do the rest. And thank you for being here. I'm going to let Dr. Seeley introduce himself so we don't take up too much time. But for those of you who know him, you know you're in very good hands. And this is going to be an amazing tour of Euclid's Elements. Anna Kate, anything else you want to say on the tech side?
Not really. Just please mute yourselves when you're not talking so we don't pick up background noise, and then try to remember to unmute yourself when you do need to talk.
Yeah, mute yourself, use the chat, speak up, have a great class, and we'll see you all soon. Thank you so much. Bye. Enjoy class, Dr. Seeley.
Oh, thank you very much. Okay, I would like to begin with a prayer. And this is one many of you are familiar with, but it's a little bit different translation. So, okay, in the name of the Father, and of the Son, and of the Holy Spirit. Amen. Come, Holy Spirit, fill the hearts of thy faithful, and enkindle in them the fire of thy love. Send forth thy Spirit, and they shall be created, and thou shalt renew the face of the earth. Let us pray. O God, who by the light of the Holy Spirit instructed the hearts of thy faithful, Grant that in that same spirit we may savor what is right and ever rejoice in his consolation through Christ our Lord. Amen. Saint Albert the Great, pray for us. In the name of the Father, and of the Son, and of the Holy Spirit. Amen. Okay, well, welcome to this tour of Euclid's Elements. I'm Dr. Andrew Seeley. I am a longtime tutor at Thomas Aquinas College in California. I have just completed, I'll be entering my 30th year as a tutor after 4 years as a student. And I just had the privilege of being able to complete the curriculum we have as a tutor. So I've taught every course in the curriculum in some iteration or another, which includes 4 years of math and 4 years of science, though my degree is in medieval theology and my dissertation was on the gifts of the Holy Spirit. So it's been a great learning experience for me. I joined the faculty at Thomas Aquinas because I love to learn and I love to teach. So that's something that a passion that I've been able to fulfill in my time there. I've also co-founded the Institute for Catholic Liberal Education, which where we're trying to share the joys of Catholic liberal education with K-12 schools around the country. So I've been doing that, and it's about a good enough introduction for me, I think. You can ask me other questions if you like at some point. And this was offering this course was connected with one of my institute programs where I do what I call an academic retreat for teachers. And that's getting together with teachers for about 3 days to do a little bit of a mini version of Thomas Aquinas College. And in the middle of that program, where we do quite a range of things from the Iliad through Pericles, we do some Descartes, we do St. Augustine, Shakespeare. In the middle of it, we do Euclid. And usually when people come to the program, the thing they're least looking forward to is Euclid. And by the time they're done, it's the thing which they find has been the most transformative for them in terms of an educational experience. Many people who felt like they were not math people, they struggled with math, found the Euclid just in an 1.5 hour session to be a fantastic experience and gave them a whole new look at mathematics. I've noticed of late, however, I've been doing that program for almost 15 years. Of late, I've noticed how bad people have gotten at being able to do demonstrations and even being able to see sort of a logical progression in an argument that you put up in through a Euclidean demonstration. And I think it's one of the things that's maybe most needed, well, it's on the top of the list or close to it for something that teachers ought to be grounded in, because it gives such a tremendous experience in actually knowing what it is to know. So I've gone lately on a campaign to try to get more and more Catholic school teachers to take some Euclid. And so when John was asking me to offer a course for the Albertus Magnus Institute, that was where I naturally turned, was to Euclid. Now we're going to, this is a tour of Euclid's Elements. So we're not going to go through this with the care that some of you know and love from your time in a liberal arts program, which where you go through almost every proposition. The day consists of, a class consists of students presenting 4 or 5 propositions at the board in the course of an hour, which they've had to commit to memory, and working that way, working through the 13 books of Euclid's Elements. Though discussion always forms an important part of that experience, the dominant experience is that of demonstrating and of developing the habits that go along with demonstrating on the board. We're going to do a little bit of that. I certainly want you all to get a taste of that. But in this course, I want to focus more on trying to understand and delve into the order of Euclid's books, the order of the Elements itself. And so we're going to do a little bit of demonstrating, but we're not going to, it takes a lot of time in class, and it takes a lot of time personally to get really good at that. So we're going to have some of that, we're going to be doing front-ending that to some extent in these first few sessions, but then after that, we'll be doing just a lot more reading and discussing of propositions and fewer demonstrations. Now, I've tried to, I'm hoping that you will get some training in that yourself just by taking the propositions as you have it in the book. And for each class, I've identified a certain number of propositions which I want you to write down separately on note paper, or use the GeoGebra to lay it out, so that you can yourself go through the process of making a presentation. And we're not going to be able to, I'm not going to be able to call you randomly, which is the common practice in a Euclid class, but I think it'll be very, very beneficial for you if you go through that process of taking a proposition and analyzing it and then representing it on a piece of paper or through the GeoGebra. And so, so I can get a look at it, I'll have you submit as I suggested for this class, submit some of the propositions in that format before class. So we'll see how that goes. I haven't done this before. I did work with a school towards the end of last year. We did a Zoom Euclid session, which had its ups and downs. I'm hoping that this format will work okay, but it is a bit of an experiment on my part. So I hope you all were able to see the sample of Euclid 1.1, the presentation of Euclid 1.1, and follow that, and see that the way in which we have the construction that you draw, and then you have the layout in one column of the steps that you go through, and then another column of references connected to each of the steps, which are justifications for each step. Did that format make sense to people? Okay, all right. So that's what I would like. Some of you were able to submit a layout of Book 1, Proposition 2 for me beforehand, and I hope you're able to do that sort of thing for the next few classes for the ones that I asked you to demonstrate or prepare. Let me see. Now I want to go into, I'd like us, I'm looking for, in a moment, I'm looking for a volunteer to do your best to present Proposition 2 for us here. And so what I'm hoping we can do is use the GeoGebra here. You have to go to the geometry one, sorry. So that's the URL for it, and you can come up here. We'll see if we have a gutsy volunteer to work us through Proposition 2. There's nothing like actually seeing the proposition go up step by step. When you have it in the book, it's all finished and complete, but you really need to see it as it unfolds before you according to the steps. And when you can do that in common with one person presenting it and everybody else paying attention to that, that is both a reinforcement of learning and a chance to notice things that you might have not noticed when you just look at it on the page or read it. Before that, I thought that, so if you can just get this site up on your own computers, that'd be good. Okay. And then also the other thing I think it'll be helpful for everybody to have up on board is this online text of Euclid's Elements, which has all the 13 books and every definition, every proposition is there. So it'll be allow us to have a common referent as we need it. So if you can get that up too. Okay. And then just to give a short introduction to Euclid. I think I mentioned this in the description of the course, but Euclid is one of those very rare things. Euclid's Elements is one of those very rare things which you can put together with St. Thomas's Summa Theologiae. They're both great textbooks. That's almost an oxymoron to have a great textbook. Textbooks are, of their very nature, they are of their very nature, textbooks are simplifications for the sake of students, for the sake of a student. So a textbook takes something which, any kind of topic which is in its nature complicated and so confusing, and tries to present it in the simplest way possible so that the student who's new to the subject can follow the argument and the development. By doing that, textbooks always cut out depth. In their simplification, they take away the depth, because they're taking away the confusing parts. That means they're taking away the depth that allows for somebody more advanced in learning to go deeper into the subject. Textbooks usually prevent that kind of thing. Euclid's Elements was put together and ordered with the student in mind, with the person who's ignorant of geometry, and leading them through in a clear, along a clear path, a clear and complete path. But at the same time, it is one of the most profound presentations of geometry as a science that exists, and it has retained its significance for 2,300 years as a work of mathematics. There's no work of mathematics, of geometry in its kind which takes the principles, accepts the principles of Euclid, that is in any way comparable to it. So he did it in the simplest and also the best way. So we're going to get to experience that as we go through Euclid. I'll answer some of those questions in just a minute. The elements, most of the propositions in the Elements are not, as far as we can tell, I mean, we can certainly tell in a lot of places, they're not original to Euclid. He wasn't original in discovery, but he's original in order, in the way in which he orders everything from the simplest beginnings to the most complex and amazing things. As you go through Euclid, we'll see some of this as in the selections we'll have in this course. As you work your way through Euclid, you start out with propositions that are page long or paragraph long, and you end up with propositions that are 6 or 7 or 8 pages long. And so the complexity of what he shows you escalates and snowballs. And it's an amazing thing as a teacher to see how students who struggle with some of these beginning propositions that we're going to do in the next few classes, by the time that they get to the more advanced propositions, are actually able to do them with much greater ease than those first propositions, where they were just struggling with the whole internal capacity to be able to understand things in order and then present them in order. So we're going to be paying attention to that and asking a lot of kind of order questions. Euclid also became the model for scientific knowledge. What does it mean to really thoroughly know something in the way that is the way that the human mind wants everything to be? So that we're going to be, we'll be able to see Euclid in his order as providing that kind of model for human knowing. Okay, so let me take a quick look at the questions that came up in the chat. I think that it's easiest, and Anna, you can tell me this if this is right, but it's easiest if we just upload them to the group page, the feed, or else you can submit them to me via a message. Does that sound right, Anna Kate?
Yeah,
Okay.
that should be good. If it goes on the feed, then everyone will be able to see it. And if you want to send a direct message, you could send it to
Okay.
you directly as well.
And then I think it's probably just fine to send a picture. I just want to make sure, I want to see the final layout. You don't have to record it. Ooh, I don't know that. That's GGB. What is GGB?
It's GeoGebra file.
Oh, it's a
So that's how
GeoGebra
you
file?
save it. Yeah, and that's why I couldn't upload
Okay.
it because it won't accept.
Oh,
I didn't know if
I don't
there was
know.
a different file we could use.
Okay. Well, Anna Kate, we can see if there's some way to work on that. But I
Yeah,
think if you do a print screen and just save it in a file, that should be fine.
Mhm.
Okay. All right. So let me see if anything else. Okay, and then we see that Euclid's Elements consists of 13 books. So we have we'll be seeing this order. We'll be looking at most of the books in books 1 through 10. More or less, it breaks down into the first 4 books are plane geometry. Books 5 through 10 address questions of, or address proportion, number, and incommensurability. And then books 11 through 13 is solid geometry. We're not going to look at books 11 through 13 at all. I think books 1 through 10 is going to be quite enough for us to try to take on in this course. Okay. Oh, sure, if you'd like to do that. Burns method of colors. Yeah. As long as you're giving the, as long as you do that kind of double column layout that I exemplified for you.
Okay, I use this method to teach it at the high school level, so I'm really familiar with the colors.
Okay, it'll be interesting actually if you submit it that we can show that. That'd be interesting to show to other people how that works.
Okay, thanks.
Okay, so let me then just ask whether there are questions about proposition 1. So I laid it out for you on the GeoGebra, and take a look here at just to recall it to your mind. Were there any questions about how that was laid out? And we do have a range of experience in terms of Euclidean experience in this class. Many of you haven't done this before. Some of you have had a year-long course in it. Some of you are masters of mathematics. Some of you are teaching it, but a lot of you just haven't had any experience at all. And I don't want to leave you behind, those who don't have any experience at all. And so please, when you're having questions, just bring them up. And as I try to tell my math students, if they're really stupid questions, then it'll take us about 15 seconds to give you an answer that you'll be able to understand, and then we can go on. Whereas if you don't ask them, then you get lost and it's kind of hopeless. So, okay, good with that. All right. Then is somebody willing to give a shot at demonstrating proposition 2 for us? And I know that working with the GeoGebra is going to be a little clunky at first, but we will be patient.
I'll give it a go.
Thank you, Morgan. I was going to call on you if you didn't volunteer. So.
Really? Well, it's a good thing I volunteered then.
Yeah.
Okay, so let me share screen.
So share your screen. Mm-hmm.
I am mildly familiar with this, so bear with me if it takes a while for me to set it up on here. Okay, so Euclid's book 1, proposition 2 is given a point and a finite straight line to construct from that point, using that point as an extremity, a new line that is equal to the line that you were given. So first we begin with a point A and a finite straight line or line segment. I'm not trying to cheat. I just want the the diagram to look mostly like it is in the book so I don't confuse you. Okay, so we're given this point which has no part A, this finite straight line B,
Oh.
C.
Yeah, but I should say, by the way, that I don't mind if you look at notes. So feel free to have notes in front of you that you're then using. Don't try to use the book. I want you to have the notes that you've taken yourself, then work from that.
Sounds good. Okay, so given point which has no part A, finite straight line BC, construct from this point a line that is equal to this line. So the first thing that we're going to do is we are actually going to join the points A and B. I do not want a full line, but
I think you can use the segment for that.
yeah.
Notice the undo features up there, the undo arrow which is really helpful.
This is your friend.
Yes.
Okay, so first you join point A and B. There's a postulate for that. The second thing that you want to do.
Actually, would you throw in the two text boxes, or what? Maybe just do it with one text box, so you can write down the steps as you go along.
Sure. This guy?
It's all the way. I've used the text box way down at the bottom.
This one.
Mm-hmm.
Okay. Okay. So you want to join point A and point B.
Yeah. Can you maybe just tab over to do the postulate you cited, or you could do another text box, whichever's easier.
I'll do it this way. Okay. So that is the first postulate that allows us to join A and B. And the second thing that we're going to do is on that line that we just joined, line AB, we're going to construct an equilateral triangle. And we know that we can construct an equilateral triangle because the first proposition of this book proved that we can, in fact, construct equilateral triangles on straight lines. So this will be interesting.
Yeah, so notice that polygon feature. She started with D, hit A, B, and then D again, and that closed it up. And then she drew random lines.
I did, because drawing is imprecise, even though mathematics is not. Okay, so
you can actually click. You can click on the other one and just keep it in the same text box.
Perfect. Construct equilateral triangle on line AB. And we know that we can do this because of book 1, proposition 1. Okay. Okay, at this point, we need to start constructing some circles. We know we can construct circles from the third postulate, so there's no issue with our ability to do so. We will construct two circles. The first circle, we're going to use point B as our center, and point C as the other extremity of our diameter. So our diameter for this circle is BC. And okay. The text box does not like me. Okay. Construct circle with B as center and BC as diameter. And we know that we can do this because of postulate 3. Okay. Now actually what we're going to do is, remember that equilateral triangle that we constructed over here on the line AB? We have the ability to extend existing finite straight lines continuously in a straight line. So we're going to continue this line DB in a straight line further down. So kind of using that as our reference. You can make it as long as you want, it doesn't really matter. It's going to go out to point E. We're going to do the same thing with the line DA. We're going to continue line DA in a straight line this way. Okay. Now, at
So I hate
this
to do it,
point,
but we're gonna be thorough with this one. So write that down to what you just did.
Yeah. Got it. Continue line DG in a straight line and continue line DA in a straight line. And we can do that from one of the postulates, postulate 2. Okay. Questions so far? Okay.
Sorry, what was the
Yeah,
tool
yeah.
you just used to do that? The last tool that you used to make the extended straight lines?
I just used the line segment tool and I started at the furthest extremity and then continued it out. With GeoGebra, you can actually be properly precise with the way that you do the construction. And if I had thought I was going to volunteer for this, I would have practiced that beforehand and done it more precisely. But yeah.
Thank you.
Yeah, you're welcome. Okay, other questions? All right. So now that we have continued those lines in a continuous straight line, you will note that this circle here cuts off that line DE. And I am going to name that point actually, where the circle intersects with that line. I'll name it G. And I will also name this point where the circle cuts off the line DF.
Sorry,
So-
Maury, is that some feature of GeoGebra or are you just placing a point?
I am placing.
You're just literally
points.
putting a point out. Okay,
Yeah,
thank you.
yes, you're welcome. Okay, so now we are going to construct a second circle. This time, instead of using the point B as our center point, we're going to use the point D as our center point. And our diameter for this circle is going to be DG. So circle the center, start here. That is our diameter. Boom.
You don't need to, that's fine. You don't have to put that one down. That's okay.
Yeah, okay, so now we've constructed two circles. At this point in the proposition, we are no longer constructing more things on our diagram. Euclid then shifts to proving that he has constructed what we have set out to construct somewhere in this diagram. So, whoops, excuse me. So the first thing that he says is, well, we know that circles have a center and a radius. And any line from the center of the circle to the circumference of the circle, each of those radii is going to be equal to one another. So if we look at this smaller circle that has point B as its center, this radius BC is going to be equal to the radius BG. I will write that down because now we are in proof section. So line BC is equal to, what was it, BG?
What's the, actually, Alexander, I think, suggested the definition. There's a definition you're using there.
Perfect, Alexander. Can you tell me what definition that is? I believe it's 10. Is that right? No, that's.
I believe
that's
it's
right.
15.
15,
Yeah.
it's 15.
Would you, Alexander, would you read that, please? Read the definition. Alex, oh shoot. Yeah, Alexander, can you read the definition for us?
Okay. Let's see. A circle is a plane figure contained by one line, such that all straight lines falling upon it from one point among all lying within the figure equal to one another.
Okay, thank you.
So because of that definition, we know that that line BC and BG will be equal to one another. Over here, need to put down a point that I haven't put down yet. Okay. So that same definition will also be able to tell us that this line DG and the line DI are also equal to one another, because D is the center of that larger circle, and then points G and I are on the circumference of that circle. So DG and DI are equal to one another, or the same reason. Now, if you look at that line DG and DI, you will note, yes, they are equal, but they have something else in common with one another. Each of those lines, as part of that line segment, contains one of the lines in our equilateral triangle. So DG has as part of it the line DB, which is one of the sides of the triangle. And then DI has as part of it DA, which is one of the sides of the equilateral triangle. Now, equilateral triangles are called equilateral triangles because all of the sides are equal. So we know DB and DA are equal to one another because we constructed it that way when we constructed that triangle in this step here. So if you have these two longer lines that are equal to one another, and they each have a part that are equal to one another, if you subtract those equal parts, what remains will be equal. And that is what the common notion 3 tells us. So common notion 3 is if equals be subtracted from equals, the remainders are equal. So equals DB and DA are going to be subtracted from the equals DG and DI, respectively. So subtract DB from, or yeah, I'll just do it this way. Subtract DB from DG and subtract DA from DI. Remainders AI and BG are equal. Is common notion 3. Questions about that? That was a bit longer of a step. Okay. In that case, I will continue. So at this point, we know that this BG is equal to AI. But that's kind of funny because didn't we say that BG was equal to something else earlier? Yes, we did. In this step here, we said that the line BC was equal to the line BG. BC equal to BG. But in this step, we said that AI is equal to BG. Well, the common notion 1 says that things which are equal to the same thing are equal to one another. So since BC and AI are both equal to BG, BC and AR are equal to one another. So BC is equal to BG, which is equal to AI. Therefore, BC equals AI. Common notion 1. Okay, so now we have this line AI equal to the line BC. BC was the line that we were given at the beginning, and our job was to construct a line equal to the line BC from the point A, using the point A as an extremity of our new line. And the line AI fits that description. So we have, in fact, constructed what we set out to construct. So then we can have our wonderful finale. to EF. Quod erat faciendum. Having done what was to be done.
Very good. Thank you, Morgan. All right,
Yeah.
questions about the steps, the way it proceeded? Is that all clear to everybody? About as clear as it can get, huh? Okay. Any other questions about the proposition?
Professor, I do have one question. I'm not sure I see why the several steps back, why the two lines needed to extend beyond the circumference of the circles. So why do we have, for example, in this diagram, DE as a longer segment? I just, in reading that just seemed like drawing those lines past that point was extraneous. I don't know if I'm missing something that's necessary there.
Morgan, what do you think of that?
So when you extend the line DB continuously in a straight line, I could have just made this an infinite straight line, just had it keep going. It doesn't matter how long that ends up being in the long run. The important part is that it's long enough such that when we do construct this small circle with the diameter BC, the circumference of the circle is going to cut that line at some point. So we are only really concerned with this line DE insofar as it allows us to have the line DG. So your point E could be way out here off the screen. Your point E could be just a little bit past. How long that entire line is not important. It's just that the circle needs to be able to cut off a portion, namely BG, that is that same radius as BC.
And that's because the definition of the circle there is that it's the circumference is intersecting a line coming off of the center point, right? So I need that line to go beyond the circumference just for the sake of it intersecting rather than.
Yes.
I don't know how to finish that sentence. I just, yeah. I
That's
mean,
okay.
when I drew my own version, I drew it to what you have as DG. I never bothered
Mhm.
drawing anything past that point because I didn't see the need.
So, right. Okay, so that's actually interesting, Joe Wetterling, because if you had the ability to construct any line you wanted, wherever you wanted, exactly equal to some other line, you could do that all day long. However, at this point in Euclid, we don't know how to do that, which is why you just throw in a huge line and then you end up cutting off only what you need.
Okay, I don't have the ability to say I'm making it that. I guess I'm kind of arguing in a. I want to say arguing in a circle, but that's a terrible pun. I'm, but I am, aren't I? To say that I'm making it the radius of the circle, therefore it is describing the radius of the circle. I'm just kind of.
Yeah. So
yeah,
so,
I'm skipping a step there. Okay, I think that makes sense.
Yeah, which gets drawn first? Does DB get extended first, or is a circle with center B drawn first?
DB gets extended first, I think.
Yeah.
Yeah. So in the steps, you continue that line before you draw the circle.
Yeah.
So then you don't know how far to put it. You draw it long enough so that the circle will intersect and cut off what you want.
Okay.
Yeah, I had done that out of order. I apologize.
Okay. And then Madeline points out BC is the radius, not the diameter.
Did I? Yeah,
I think you've been saying diameter
Yep,
most of the time.
that is true. I'm sorry, I still have summer brain happening. Okay. Yeah.
Other questions? Okay. Does anything strike you from having watched it be laid out like that you didn't notice before?
One thing
Okay.
that I thought was really cool about this GeoGebra thing is I was able to realize that you really can shift all these points wherever you want it. Like A and BC, I guess, point A and line BC. And that you can almost have an infinite length of BCs any way you want. You can still make this prop work. I don't think I realized that.
I'm sorry, can you explain a little more?
Sure, yeah. So basically, I could have my point to the right instead of to the left like Morgan had it. And yeah, thanks Morgan, the J. And then like you can make a, yeah, exactly, a KL as big or as small as you want it. And you can still do that proof. It'll look different from what's in the book, but you can still do it. And that's one of the reasons I think that it's helpful to extend LK or what, not LK, sorry. You know, the BG, we were talking about the extension down to E. It's helpful to do that because if you are using different lengths, like let's say LK is really big, you may not be able to reach it. I was just messing around with it earlier and I realized, oh, I don't know why I didn't think about this when I was in school because I didn't.
That's one of the things that if you have time, you want to play around with that. Put the things, so Morgan was careful to make it look like the diagram in the book, but it's really helpful for these propositions to get a better grasp of them, that you set them up in different places and see if you can follow the construction. Ooh, nice. Cool. See if you can follow the construction, even though the diagram looks very different than the one in the book. And also you can mess with the letters, like use different random letters to try to dissociate yourself from focusing on the particular diagram in front of us that's given to us in the book, and to be able to really see it in its universality. So thank you, Morgan.
Professor, to that end, one advantage of my not extending that line as far as I should have and just kind of skipping ahead and making it the diameter, or radius rather, now I'm doing it, making it the radius, was that my lettering was off from the diagram. So I had to keep referring back, and that made me step through it a lot more carefully, because I couldn't just copy the lettering out of the book. I had to go look what mine was. Because I had to really understand what I was talking about and not just kind of blindly type it out.
So
I'm not advising to skip a step like I did, but the different letters, like you said, was very helpful.
and it messes you up when you're doing this at the board. You'll often have drawn it in a funny way, and so you look at it and you get lost. So let me step back for a second. Morgan, you stopped sharing your screen. Could you bring it back, or do you destroy it?
I can bring it back.
Bring it back.
Here we are.
Okay, so given what Morgan just did in the argument, do we now know that, okay, we will be able to place at point J a line equal to LK, even though they're in different positions? Or you might take J and put it a lot further away from K. Do that. Morgan, can you take J and separate it some distance from K? Okay. do we now know that we can actually take LK and put it at J? Is there any question? Does anybody have any question or doubt about that?
I mean,
Now,
Professor, to put it in very kind of modern terms, and not to put Morgan on the spot with this, but in theory, we could grab that diagram on the left that she completed and actually drag and resize it and turn it and fit it to that. It is, it's a general principle. We're just looking at one example of it. And then, not that you're going to make her very, very upset at all my suggestions here, but in theory, that should work. So I suppose in pre-computer times, we'd have to go through the whole process again, but we could do that. It would just look, like you said, it would look different as she's doing.
So one of the fascinating things about these Euclidean demonstrations, and it's very easy to get to have a Euclid discussion drift off into philosophy and never return, is how is it that by following what is a very particular and unique presentation, how do we see that now we can do it anywhere at all? So there's this jump from the particular, which is what we're following. All of the argument is about the particular thing that she's drawn, and yet the enunciation is about anyone at all. So how do we go from that particular one to knowing anyone at all? And let me keep that in mind. There's I want to talk a little bit just about the breakdown of a proposition, and I'll come back to this point at the end. But Morgan did a nice job in pointing out that you almost as though you've taught this before, Morgan. Morgan did a nice job in separating out elements of the proposition. So every proposition begins with an enunciation, an enunciation, not an enunciation, but an enunciation, which states what it is that we're to do or to prove. And then immediately you get a particularization of that. So proposition 2, to place at a given point a straight line equal to a given straight line. So that's this universal instruction. And then the first thing is, let's make it particular. Let A be the given point and B, C the given straight line. So now we've gone from this general thing to do to, we have to now put B, C, this particular line, at point A. Then, as she distinguished, then every proposition is going to have a construction part where Euclid is saying, okay, now we're going to do this, and then this, and then this, and then this. And the diagram comes into being through that. And then once he's finished the construction, then he needs to go and prove that what he's constructed is what he said, what he wanted it to be. So there's the universal enunciation, the particularization, the construction, and then the proof that this is what we want it to be. And then he gives us then he is able to draw his conclusion about it at the end. So that's a regular pattern, and you should look for it when you're taking on new propositions. It's really helpful to just outline it that way and distinguish those parts of it. Now, I want to point out, if we look at proposition 4, okay, Morgan, I'm gonna, if you can, yeah, let me go ahead and throw this up here.
Actually, a quick question, Professor.
Sure.
So just in terms of like the pedagogical kind of process here, like this is actually kind of a complex proof for proof 2, right? I mean, we have really like what, 4 circles when all's said and done, like a bunch of different relationships between 2 different sets of radii, like, so how does that fit in with what you were saying earlier about this sort of being an elementary textbook? Like that isn't what I would do.
Okay, let's come back to that. That's a great question, a very natural question, one that comes up often with Proposition 2 in some form or another. I want to point out with Proposition 4, though, in Proposition 4, which is, this is not a construction. He's not telling you to make something or do something. He's making a claim about something. So if you have two triangles, have two sides equal to two sides respectively, and the angles contained by the equal straight lines equal, then they also have the base equal to the base, the triangle to the triangle, and the remaining angles equal to the remaining angles. So in this one, where he's trying to demonstrate a truth rather than make a construction, he still has the same basic division: the general enunciation, the particularization in the triangles A, B, C, and D, E, F, which have to be drawn. And so when they're drawn, they have a particular look to them that other people, if you just drew it, you draw different looking triangles. Then there is a construction phase, which in this one starts at if the triangle ABC is superposed on the triangle DEF. So it then tells you how to do that. And he makes them coincide. Then he says, then he makes his proof part, which would be, well, since they're coinciding, they're equal. All of that is in the particular. But then he draws a universal conclusion. So he says, therefore, if two triangles have two sides equal to two sides respectively. So he's basically restating the enunciation in its universality. So he goes from the universal to the particular, the constructions in the particular, the arguments in the particular, the conclusions in the particular, and then he draws a universal conclusion. And in many texts, and I'm not quite sure what your text has, in many texts, rather than the universal restatement at the end of this kind of proposition, they just say, therefore, etc., saving precious ink. But Euclid didn't save precious ink. Euclid, I think, wrote it out every time, that universal conclusion. So it's remarkable that he's getting to the particular conclusion, but then he also always draws the universal as a separate statement. So if you ever see therefore, etc., that's what's going on. Okay, so let's come back to, sorry, is that Luca? Was that your question?
Yeah, that's me.
Okay, so let me see if I can pull up Proposition 2. So you said this isn't the way you would have done it. So if you were told to place a straight line equal to a given straight line with one end at a given point, how would you do it?
Well, I mean, it's not that I would have done Proposition 2 differently, right? Necessarily. But something like Proposition 4 seems much simpler in a way, right? It's just pretty much I forget which postulate it was, but the combination, the combination 4, right? It's just like an application of that I guess it seems relatively straightforward. Whereas this has, it's really hard at first to see how actually this works, right? Proposition 2, and there's all these relationships. Like, you have to keep in mind, really 4 different sets of things, right? So I guess I was just wondering, pedagogically, like I could see someone saying this is a little too difficult at the beginning. I don't know though.
What do others think about that? So, I mean, there are 2 questions you might ask, and I'm not sure which one you're focusing on. One is, if Proposition 2 is so complicated compared to some of the others, why does he have Proposition 2 as the second proposition rather than something simpler? Right. Another question would be, does Proposition 2 have to be so complicated? You're asking the first one, I think. Is
Yeah.
that right?
Oh, absolutely.
Okay.
Yeah.
Yeah. So why do you think Euclid has this as his second proposition? Is this pedagogically bad?
Yeah, I don't know. I mean, I could see reasons like I guess we're thinking about the rhetoric of it now. I could see rhetorical reasons for why this might be good, right? There's something a little bit astonishing about it. It's also something that seems so simple, right? Just essentially replicating a length. You realize how much actually goes into it if you and once you see the sort of inescapable necessity of it, there's a lot more that goes into that than you might think. So maybe that's maybe a reason that comes to mind at first.
Okay. What do people think about that?
Shock, maybe a bit of shock and awe.
Yeah, this is actually meant to scare you away.
I think, Professor, there's a little bit of the same feeling as reading that Aquinas describes the Summa as an introductory textbook. You know, you look at that from the modern perspective and go, really? But I wonder if it's not in part just because he had to. Like I suppose I'm modernizing the whole thing of picturing him sitting there, you know, with his Microsoft Word, you know, version of this where he can cut and paste things around. But as he was thinking through this, perhaps there's a necessity. If he's going to use a particular proposition later, it has to come before. So there's a certain, I don't know if that answers the whole question. There's probably pedagogy to it too, but there's a certain perhaps logical necessity to at least some of the sequencing here. But I don't know if that answers the whole thing. I'm just starting it new myself, so I've only read, you know, so far ahead. I know he uses, I believe he uses this in the next one, if I recall correctly.
In proposition 3?
In proposition 3, if I remember.
Right, but he doesn't use it in 4, right? He doesn't need it in 4.
Oh, right. So could he have put 4 before these?
Exactly.
Yeah.
Is it possible? Sorry.
Who's trying to talk?
Go right ahead, please.
I was going to say, is it possible that he is putting propositions 2 and 3 following 1 for the pedagogical reason of you should be used to how these constructions work? Like, okay, we're going to do prop 1 and construct this equilateral triangle. Also, like in geometry, we do constructions and this is how we do them. So kind of like just getting people used to the idea of this is how it works. I don't know. I just thought of that. I don't know if that has grounding.
Okay. People saw that in proposition 3, given 2 unequal straight lines to cut off from the greater straight line equal to the less, proposition 2 is allows him to take C and immediately stick it on A somewhere, or a line equal to it, AD. So he does use proposition 2 to do proposition 3. What about proposition 4? So first of all, I guess, are there questions about how about the argument in proposition 4, about what's going on there?
Maybe this is stating the obvious, but part of me wants to know why he's letting everything coincide in 4 and doesn't just do that in 2. Because it almost feels like a copy paste thing. I know that sounds weird and maybe I'm missing something, but that's what I was thinking.
Okay, so what do we think of that?
Well,
This actually is 2.
For number 2, you're actually proving that you can draw a line, but for 4, you're just proving that 2 shapes are the same. So that's why you can't use this the supposition for 2 like you can for 4.
So he's basically using 2 without saying he's using 2.
In proposition 4? I was wondering that. Is that what you were saying, Madeline?
I thought it was kind of the opposite, why you can't use the tactic that you use in 4 in proposition 2. I thought that was the question.
Okay, so make your point again, please.
Well, for 4, you're just being asked to prove that if you have 2 triangles, that they're with certain things equal, then everything else is equal. But in 2, you're actually being told in that like in the general enunciation that you can actually draw something. So you're actually being asked to draw something while you're not being asked to draw something in 4.
Mm-hmm. So that the yeah.
I was going to say, if I could interject, the way I'm looking at this, it's almost like 1, 2, and 3 are ways to construct things, and he's grouped them together, and then he moves on to doing in 4 a proof that, you know, if you've got two lines of equal size and they form a triangle with an equal angle, then you've got equal triangles. So essentially what he's doing is he's constructing things to show, okay, this is how you can create something, and then you need to use those creations in proofs. And I guess you'd have to know what goes on in 5, 6, 7, etc. to really get to that point. But it seems like he grouped them together specifically because they were ways to construct things like an equal line.
Mm-hmm. So let me see if I can press Erica's point a little bit, which I think connects with what Tom is saying, is that it's right that in proposition 4, he's not telling us to, the general enunciation is not to construct something. It's something is true. If you have 2 triangles with 2 sides equal to 2 sides and the angle contained equal, then all the triangle and all the elements of the triangles are equal. That's just a statement of truth. But there is a construction contained in it. So after the first 2 little paragraphs there, which are particularizing the enunciation, he starts out the construction here by saying, if the triangle ABC is superposed on the triangle DEF, and if the point A is placed on the point D, and the point B also and the straight line AB on DE, then the point B also coincides with E, because AB equals DE. So he's saying he wants you to take the triangle ABC and put it on top of EDF, but he doesn't just say pick it up and put it on top of it. He does it first put one point on top of another point. Then you can get the whole line, the whole of one side of the triangle lined up. And then he says, once you do that, then he shows you that everything else is going to coincide. So there is this implicit construction part where he's saying, pick that point B, put it on E, and then make sure that BA falls on top of ED. Then once that happens, and everything else coincides. Does that make sense? So what I thought what Erica was suggesting was that is implicitly relying upon proposition 2. Because you have to be able to move, you have to be able to put one line on top of another line. And to do that, you're going to have to use the kind of construction that was offered, that was given us in proposition 2. What do we think of that?
All right, I do think you can still do proposition 4 without using 2, although I think using 2 will be easier. I mean, knowing, and I've done proposition 2, you might have better grounds to do 4, but I do think you can still do proposition 4 without having 2, and I'm not sure if it'd be easier or not. Like I think it was Luca's question asking why is that order, and if you cannot have 1, 3, and then 4, then not have 2 in that sense. Although you need 2 for 3.
How do you do 4? Yeah.
Well, I believe you can do 4 if you have you have the enunciation. I don't know where you would have. I don't believe to have both triangles you would need to know proposition 2 to draw it out at least.
Okay, but what do others do? People think? Do you think, as far as you can tell, that yeah, this idea of picking the one thing up and putting it on the other is not in any way connected. It's not really dependent upon what he's doing in Proposition 2. It's just another thing we might be able to do.
I think
it's just a separate thing. That if you look forward ahead, he's going to get into a lot with triangles, and I think that Proposition 4 is just like kind of changing the subject. Now we need to look at this, and we're going to be using that a lot going ahead.
Interesting. Okay.
Because isn't triangles A, B, and C and D and F like a given? Like that's what he gives us, right? We don't have to prove it. So, I mean, and he tells it what type of triangle it is too. So, yeah.
What do you think, Erica?
Well, I mean, it's fair that he already has the base equaling, sides equaling. So technically, I mean, it makes me think of like a stick. You know, he could get a stick, just put the stick, same stick, move it over to the other thing. I mean, that's how it feels like it's happening. But I can't remember who it was that said it now. It was someone earlier said that you can do with Proposition 2, it's a construction. People were saying you could split the first 3 props in construction and this prop for not construction, basically. And that's why I thought of it maybe using that, but that's only if we wanted to beg the question and say, well, because Professor Seeley was saying the point A is mentioned first, I guess you could say from point A construct the thingamajiggy equal to the other thing, but it's not needed for the prop necessarily, because technically we know everything's equal. But I don't know. I think both sides are interesting to me.
When he says that if the point A is placed on the point D and the straight line AB on DE, are we thinking of that as, I'm just going to do that in my imagination. I'm just going to kind of pick the one up, put it over here, and then lay the line along and bring the whole triangle with it. Is that a sort of the way we're thinking about it? You're just doing it in your imagination like that.
Yeah, but the thing about it is that if you think about it, that's how I feel about it with the computerized world. The way Euclid did it, he must have had to create D and then draw E separate from AB in a non-computer world. I don't know.
Yeah,
sorry.
So, Professor, oh, go ahead, please.
Well, I was gonna say, it sounded like Erica, like you were sort of questioning whether or not this whole motion, like moving the one onto the other, is really, like, I guess, a proof at all. Like the sort of first thing that you said, like it just sort of sounded like you had a bit of an issue with that. And I guess I'm kind of maybe having the same issue, if that was right, what I heard, because this almost seems more of just like a postulate to me, you know? It doesn't really seem like a proof at all. And I don't know, Professor, it seems like once you start introducing motion into things, you're not really doing geometry anymore. And you've sort of left the world of the forms, as it were, and we're doing physics.
Okay, what do people think about that? That this looks like a physical argument and not or a physical thing you have to do, rather than the kind of logical step-by-step proof that we had in 2.
The only citations are common notion 4 on Proposition 4. He doesn't actually combine any 2 previous things. He's just kind of expanding on what he said in CN4, which is things which coincide with one another are equal to one another. There's nothing new or anything being put together.
Yeah, it's interesting. Now, let me just, a warning about the references. The references are not in Euclidean manuscripts originally. I'm not quite sure when they came in, But those are editorial additions to help the reader. So Euclid didn't actually make those little marginal or bracketed references. So it's you just have to be cautious about how much you can rely upon them in terms of understanding what Euclid is doing or what he's expecting us to rely upon. So
Sorry.
it looks like this is a standalone proposition. It's got its own sort of physical motion thing going on that's not really related to any of the propositions before, nor is it related to any of the postulates at the beginning. Is that right? It's almost as though you could have started this one. This could be the first proposition. Which then, I guess the original question was like, shouldn't this have been either the first or the second proposition? Because it seems like a much simpler kind of argument than the complex argument that we get in proposition 2.
Professor, the thing that's getting me is if we go back and I'm Euclid, thousands of years ago, and I'm demonstrating this, or I'm one of his students and I'm demonstrating it back, and I'm drawing this out however I can. I don't have modern tools, so I could be doing this with sticks and string and sand if I wanted to, or pencils and paper now. But if I'm doing that just at the beginning, let A, B, C, and D, F be two triangles, having two sides, A, B, and AC equal to the two sides, D, E, and DF. So if I want to actually physically construct them equal, I mean, I guess in the real world, I can just take a stick and say, this is the length, and I'm going to trace that both times. But if I want to be more mathematically rigorous about it, proposition 2 is the way I do that, because I can take a point D and construct a length DE that's equal to AB. And we know how to do that now. So I don't know if there's an implicit kind of how to set up. It's not necessary as far as maybe the logic of the proposition, but it's maybe necessary in the setup, if that makes any sense.
Okay, if I'm getting it, you'd be thinking that is this right, that proposition 4, the argument involves the superposition, the moving of one on top of another. Proposition 2 has already shown us how to move one line so that it goes where we want it.
You're giving me slightly more credit, but I'll take that. Yes.
Okay.
I was slightly less sophisticated than that, but yes.
Okay. Yeah, that's one of my favorite tutors when I was a student, Richard Ferrier. He was always excellent at that. You'd say something and then he would smile and say, "Oh yes, is this what you're getting at?" And it's like, I have no idea where that came from, but it's really, I really love the beauty of it. At least, so proposition 4, I think, in its argument presents the problem that we've brought up, which is it looks like it's a standalone and it involves picking the one triangle up and moving it onto the other, which seems grossly physical and not like this, not like the logical step-by-step thing that we've seen in the first few propositions. Also, there's no postulate that says you can superimpose things. And if there were, then couldn't we just have done that? Couldn't we just done that in proposition 2? So another criticism that would come up with proposition 2 is, isn't this vastly complicated? Couldn't we have just said, okay, I want BC to go on A. Well, I'll pick up BC and I'll just move it over there, and just like that, just like in proposition 4. Or if you wanted to use a compass, couldn't you just take a compass and put the point on B, make it length BC, and then pick that compass up and go over to A, and then you've got the line where you wanted it to? That seems so much simpler than the complexity of proposition 2. So
Professor,
so then, yeah.
Sorry, is this one, is me, Joe, sitting here with my compass on this particular piece of it, is that as generalizable as proposition 2? If I sit here and I just say, you know, I'm going to use this particular compass to manufacture that physically in front of me, is that as, I don't know, it feels like proposition 2 is giving us something more, well, less physical, certainly. Maybe that's getting into, I'm getting too philosophical about it, but it seems it's more, less tangible, less physical, more generalized, perhaps, than just saying it's describing very technically what we would be doing with that compass and just demonstrating that it mathematically makes sense.
So what do you think about that? Do you think, is proposition 2 unnecessarily complicated? Because you could just do this with a compass or a measuring rod or something. You don't have to do it with these the complex dance with the circles and cutoffs. Or would you say, no, you have to do it this way because otherwise you'd only know it for your particular compass and you couldn't universalize it?
I think you do have to do it this way because you're picking a random point A, and it's not, it's certainly not the center of a circle, at least in this diagram. You need to put the circles there and cut them off and build that relationship in order to get the proof. I don't think you can get the proof that these two lines are actually equal without doing that.
Yeah, you could do probably several different operations on the specific triangle in front of you and say, okay, like this seems to be true about this triangle here. And then if you get another triangle, you can do similar things. Say, okay, so that same thing that was true over here now seems to be true over here with this second triangle because I'm doing it again. But that's kind of like reinventing the wheel every time. In some cases, literally. Whereas with proposition 2, in a way, you're sort of front loading the complexity so that you are able to have the knowledge that the second proposition brings universally. So you can just always know about every triangle that proposition 2, or not triangle, but or in proposition 4, it would be triangles. But you can know, what am I trying to say? You can know universally that every instance ever is going to have this truth about it because of the work that you did in Prop 2.
Picking up what Morgan just said, when the first time I studied Euclid, which is a few years ago, when I did preposition, I mean, Prop 1 was pretty simple. And then preposition 2, it's a big step compared to preposition 1. And I think if you want to get a pedagogical sense, what was the original question that Luca asked was that at preposition 2, at least, you have an apostolate there, you have definitions as well, you have common notions. So it gives you like an idea of like a whole of what Euclid is doing. It gives you trust in Euclid and what he's doing to a degree. It's a very superficial way of saying it, but at least in my experience when I first did it, I began trusting Euclid, I'll put it in those terms, when I did preposition 2, because you see that, the self-evident principles, which he lays down at first in the introduction or before the book actually begins, you're like, okay, his definitions, they make sense. Common notions, they also make sense. But then until you actually experience preposition 2, you start realizing why it's so important to trust him. And if you had preposition 4 before 2, you wouldn't get that notion. That's one of the reasons I would give. It might be a bit of a stretch, but that would be at least one of the reasons I can see why preposition 2 would be before 4.
To help you trust Euclid more?
Well, not only trust him more, but also see the definitions and the common notions and what he says makes perfect sense while you're trying to prove his denunciation, whatever that might be. So you see a logic behind it.
let me leave this where it is. There's, I mean, in these kinds of discussions, we see different positions you might take and different reasons for it. Can't resolve a lot of them, especially since Euclid doesn't offer any commentary. He's just doing his thing, and we're trying to figure out the thought behind it, and he doesn't give us anything in that regard. I think that one position it looks like would be laid out is that Euclid seems to be proceeding not in the best pedagogical order, because proposition 2 is more complex than proposition 4, and proposition 4 doesn't rely upon proposition 2. So why is he putting it later? It seems like he ought not to have done that. A possible answer to that would be proposition 4 involves a moving line. It moves whole triangles, but it moves it line according to the sides first. And proposition 2 actually gives you an argument saying that you can do that. So perhaps there's an implicit, at least, reliance upon it. So let's leave it there, though. Maybe this would, if you follow that second line of reasoning, you'd say to Luca's original question, it's not that the argument here, Euclid isn't thinking the argument, I'm going to give you the simplest arguments first, but I'm going to give you the simplest enunciations first, or I'm going to proceed according to the basic steps, or the simplicity is in the enunciation and what I'm trying to do, even though the argument to do that may be more complex than other arguments, yet what I'm trying to do is more fundamental. So to place a straight line equal to a given straight line at another point, I have to do that first before I can do other things. But I want to go and take a little bit of time just to talk about the opening parts, the definitions, postulates, and common notions with which he starts. And there are 100 questions that I could ask about this. Let me start by, yeah, I'm going to start just by asking, what seems to be the difference between the definitions, the postulates, and the common notions? Why do they seem to be separated out that way? I'm going to stop sharing so that I can see all of you at once. Oh.
But I guess broadly, it would seem that common notions don't necessarily belong to geometry. So they're really philosophical notions, right? So that's a difference. Whereas it seems like definitions do properly belong to geometry, even though they can't be established by geometry, right? So I guess that would be.
Would you say it's like observations of geometry? Is that what you were thinking, Luca? Like that they weren't exactly geometry, but they were like what you could observe from it?
No, well, not really. I mean, like geometry, like it seems like saying that a point doesn't have any parts, right? Is that which has no part? That's not something that geometry could ever hope to establish. That's a philosophical notion, right? That has to be given before we begin the discipline of geometry, right? Because we can't do anything without points or lines. Same with a line, like that has to be established by, but it's something that properly belongs to the discipline itself. Like that's not something that belongs to necessarily to metaphysics, right? It's something that really properly belongs to, whereas the common notions do, right? Those are real, those are just broadly speaking things that need to be true for like any endeavor, really, except maybe 4. But that sort of seems broadly to me to be the distinction. I don't know. Is this what you're asking, Professor?
At least it's an answer. It's a possible answer. So common notions. The first one, things which are equal to the same thing are also equal to one another. I think, Luca, you're saying there's nothing particularly geometrical about that. That's a truth that can apply in many different subject areas, many areas of thought. You might apply something like that. Do we think that's right? Whereas a point, that's the kind of thing that belongs to geometry.
I see common notions almost as logical things. If you have two things that are equal, they're equal. You know what I mean? You see? Whereas
they're very foundational, like the principle of non-contradiction. These are ground. If you don't agree with these things, we aren't working in the same world.
So foundational to thinking, not particularly foundational to geometry.
Yeah. Well, by contrast, like in the get my terms right here. In the definitions, he's defining the way he's using those words. I mean, he's not speaking English, obviously, but his use of point, I'm making a point right now. That's a different use of the word. If we're talking about it, I have to make sure we're not using the terms in different ways. With the common notions, you either accept those or you don't. If you think two things, if you think that a part can be greater than a whole, then we're not operating in the same logical structure here. That's beyond mathematics. I think that's kind of foundational to the universe. Is it universal, perhaps I could say.
right, what I was trying to say is it's a step in logic, the common notions. Common notion one, things which equal the same thing are equal to one another. That's a logical conclusion. If equals are added to equals, then the wholes are equal. Again, it's a logical conclusion. So
what do you mean by logical?
Is it?
It means that it follows the steps of logic, that one thing results from the other. If you have two things that are equal, and then something else is equal to one of those two things, it must be equal to the other of those two things, is just common logic.
Okay, Anthony?
No, it just seems like when you say common notion, for me, at least when I first read it again, it seems like there's self-evident principles, right? So I mean, I don't think you can prove that a whole's a whole is greater than a part, and then you obviously have to define what is a whole, define what's a part if you want, and so forth. But I just believe that let's get the first common notion I'm reading here. Things which are equal to the same thing are also equal to one another. You can try to explain that. Even if you get a little kid, you can show him a piece of pizza and then show him, look, this piece the same size as this piece, which one is greater? And the kid, he's not going to be able to answer. He's going to say they're the same. But in abstract, when you don't have something physical, which is harder, obviously, I think it's just a thing of like self-evident principles. You can't really try to. I mean, there's no way if someone doesn't understand there's something greater and smaller and so forth. It's just one of those things that human mind grasps because of self-evident principles. And like even like Lucas said, again, you can't. It's hard to prove. I don't think you can prove that specifically. You just take it as a given, and that's why Euclid just lays it down as a given. You might be able to explain it later on.
Okay, so I'm a little confused. Are you thinking that, say, for if equals be added equals, the wholes are equal? That's something that a little kid can see to be true. Is that what you're saying?
Yeah, I'm saying it's a self-evident principle. Yeah, a fact.
And is that, Tom, kind of what you're getting at? It's logical. You immediately see the necessity of this being true.
Right, or it's an if-then kind of thing. If A plus B equals C, if A equals B and B equals C, then A must equal C. It's a logical argument.
Okay. Let's see. So I think there have been two things that have been proposed, at least that I'm getting, about how the common notions are different from the definitions. One is that they're statements that don't seem to apply simply to geometry, but apply more broadly to areas of thought. Maybe they're even foundations of all thought. The second is they're things which once they're stated, you immediately see they must be true. It seems like a logical necessity. Little kids can see these things to be true. So Ron, are you going to confuse us more? Common notions are definitional. Okay, can you unmute and explain that, please? Or is this something you'd rather not do? You'd rather not unmute?
You might not have audio.
Oh, okay. Okay. So common notions are definitional and they draw inferences from things that are defined commonly. So I guess what's confusing me is, are you saying common notions are like the definitions? Or are you thinking they're a step beyond the definitions? And they proceed from definitions that everybody, whole and part, are things you don't really have to define separately because everybody gets that? Okay, so it's interesting. That is an interesting point. He does not define whole, part, equal. He doesn't define addition or subtraction. He doesn't define coincidence. So these are the terms in which these statements are made. He doesn't feel like he has to define them, though he does feel like he has to define point and line and surface and things like that. So that's another interesting difference. What about the postulates? How do the postulates seem to compare to the definitions and the common notions?
I think it was Luca who said at the very beginning of this part of our conversation that the common notions are very general and seem to be applicable to multiple sciences. The postulates, on the other hand, seem to be particular to the science of geometry because, like, they are concerning geometrical things explicitly.
Okay, does that seem right? The postulates are about geometrical things. The common notions, it's less clear that they're about geometrical things. Or it seems like they're not simply about geometrical things.
Yeah, it kind of also seems like perhaps the difference then between, so if that's true, that common notions are about other things and postulates, or can be about many things, and postulates are more properly geometrical, is there a distinction then between like a postulate, which seems to be almost a constructive kind of idea, to draw a line, to describe a circle, and the definitions, which seem to be more theoretical kind of materials? So we have the same perhaps bifurcation even here in our first principles that we see in the later proofs, right? Where some are constructive and some are theoretical. Is that, I don't know if maybe that's the distinction that we're seeing here.
Okay, so that's agreeing about the postulates versus the common notions. The postulates are a property of geometry, common notions are not. In that regard, connecting it to Ron's point, the postulates involve terms that he's defined for this in the definitions: straight lines, circles, right angles. All of those have been defined previously, whereas the terms in the common notions haven't been. But then how do the postulates differ from the definitions? The postulate seems to be constructive. The definitions seem to be theoretical. That's what Luca's suggesting. What do we think of that?
I can't say that I disagree. I am just like hesitant.
You really want to. You want to disagree.
I just really want to argue with somebody.
Yeah.
No, I can't say that I disagree, but I will say I'm not sure why, but I'm a little apprehensive about that word theoretical. I guess, Luca, can you maybe explain how you're using that word theoretical for the definitions and why you think that they don't apply to, that does not apply to the postulates?
Well, I guess I was thinking when you look at the propositions, right? There are some that are demonstrative, right? And there's some that are constructive, right?
So are you thinking there propositions 1, 2, and 3 are constructive, proposition 4 is demonstrative?
Is demonstrative, right? Yeah.
Okay. That does,
And,
yeah.
Sorry, yeah.
I was just going to say that does correspond with the conclusions of, and I don't know if people notice this, but the conclusions of 1, 2, and 3 are being what it was required to do. The end of proposition 4 is being what it was required to prove. So they end differently. And then Morgan, when she demonstrated 2, she ended at QEF, which is the abbreviation for quod erat faciendum, which is being what it was required to do. And QED is quod erat demonstrandum, what it was required to prove. So that corresponds to what Luca's saying about 1, 2, and 3 being constructive, 4 being theoretical, demonstrative. That's what you're thinking? Okay.
So I guess maybe you're right to push back on that, Morgan, because I guess I was thinking that if we do have that bifurcation between those two kinds of propositions, then if you have these postulates that are to draw a straight line, to produce a finite straight line, those are kind of the givens that you would need to do constructions with, right? So you look at the proposition 1 and it's just starting from the postulates as constructive. Now the definitions are need to be there too, right? But there does seem to be something particularly constructive about the postulates, whereas the definitions are, as it were, in the world of the forms, right? They just are things, right?
Yeah. Sorry.
Yeah, no, that's, yeah.
Oh, so the definitions seem to be saying this word means this thing, or these are what things are, not necessarily with an eye to whether or not they exist or how they are made. The postulates seem to be saying you have the ability to do this, or you have the ability to say that this is true, as is the case with that 5th postulate, which is a whole nother can of worms. Point being, definitions are just kind of factual, it seems. This is what this is. And then the postulate is sort of like an action card in a card game or something. Like, yeah, you can do this now. You can say this now.
But
There's
what do we do with 4? With postulate 4?
That was going to be my question.
Oh.
Yeah, I
Actually,
think
even postulate 5. So if you look at the postulates, they almost
Mhm.
seem to divide the way that Luca was pointing out the propositions do. The first 3 are to draw, to produce, to describe. Those are actions. Those are like something like the construction, the constructive. But 4 is that all right angles are equal to one another. That's more of a statement, which is like the proposition 4. And then 5, that if a straight line falling on 2 straight lines make the interior angles on the same side less than 2 right angles, the 2 straight lines, if produced indefinitely, meet on that side in which the angle is less than the 2 right angles, on which are the angles less than the 2 right angles. That also seems to be just a statement.
Well, you do have the production, right? There is the producing them indefinitely, right? So there's a sense that there's some constructive aspect there, but you're right. 4 seems more like definitions like 11 or 12 or something, right? Like,
Actually,
Yeah.
I think I kind of clicked in to look at the definition in terms of what it's getting at. In the definition of a right angle, it is clear that the two angles at the foot of the perpendicular, such as angles ACD and BCD are equal.
Can you share your, are you looking at the screen?
Yeah, I am.
Could you
Let's
share
see.
it with us, please?
How do I share a screen?
Down at the bottom.
Okay,
Yeah.
I might have to put this, I'm on multiple screens, so
Oh. Okay.
let me just put this on this screen. And then down at the bottom. Video, FaceTime, virtual. Share screen, there we go. Nope, I guess I didn't want to do that.
I think if you click the share screen button, you'll have an option to like just share one window.
Yeah, it'll allow you to pick the window you want to share.
Desktop 3. Is that sharing now?
No.
Nope.
Oh, wait, there we go. Resume to share your screens. Okay, hang on. It's not letting me do it because it's in my system.
Okay, well, go ahead and tell us what you tell us. Go ahead and keep making your point, and we'll see if we can find what you're talking about.
Okay, so I guess my point is that when you actually look at postulate 4 in what it is, it's telling you how to produce two right angles that are equal to one another.
So you think it is constructive?
Yes.
Do we buy that?
I don't
do.
think it is. Go ahead.
No, you're smarter than me.
No.
Go ahead.
No,
No,
no.
okay,
That
I am
is
not, and I've been
acceptable
talking
to-
too much.
Listening to you, Morgan.
Yeah,
No,
Miss Wood or Mrs. Wood.
Yeah, that's my little nickname because my name's Brittany Woodcock and my husband calls me B Wood, so that's what he
Okay.
put on my phone. So sorry.
Okay, Brittany, go ahead.
So I have spent a little time with quantum mechanics and stuff. That's not related to this, but when you say theory, that's what I think, like something that I can't go out in space and prove it. So this we could actually see how it works. So I do get what Luca is saying as well, and what others are saying as well, that it's what is it? That's like more of a statement or what have you, but also that this can be produced. So this is far more exciting than any of the math that I ever did in public high school. And
We're just getting started.
Yeah, I just wish I would have had something useful like this, then I wouldn't have hated math. So, but anyway, but yes, I buy it. Thank you.
Okay, so let me, I thought, is this what you were suggesting, is that theoretical to you means something that's different than real or manifest? It's a theory.
Yeah, I'd say
And you can't,
manifest.
yeah, okay. So
Because you might be able to prove it in the future, but as of right now, you can't.
Now, Luca, you weren't intending theoretical that way, right?
No.
Okay.
Yeah, I think I was intending it in, I guess it'd be a more philosophical sense, which would be something that like you'd say that something that must be true all the time would be something theoretical, right? I don't know. Sorry, I'd have to think about it. It's something that I think Professor, what you said exactly was right. It's something you can see, like with your mind, as it were. That's why it's called theoria. So that's very different than the way that it's used in like modern experimental science, right? Where you come up with something that might be true if you test it. So
it's a theoretical in that way would be, this is a statement that is being asserted as true. it's not telling me to do something or giving me a power to do something. It's just in itself a statement that I'm supposed to say that that's either true or false. Is that right?
Well, it
Luca, is that
definitely
the way?
makes sense as
Okay.
to say philosophical. I understand more. So
Okay, so then if we go back to postulate 4, that all right angles are equal to one another. Does that seem to be sort of something that's stated as philosophically true, as being a sort of philosophically true, or is this something that's supposed to empower us to be able to do something?
That seems to me to be a very specifically theoretical statement. That seems to be a statement yeah.
Whereas to describe a circle with any center and any distance, that's more like empowering us or giving us an ability. It's interesting to compare, and as I think Tom was doing, compare postulate 4 with definition 10. When a straight line set up on a straight line makes the adjacent angles equal to one another, each of the equal angles is right, and the straight line standing on the other is called a perpendicular to that on which it stands. There's a definition of a right angle. How does that compare with postulate 4, that all right angles are equal to one another?
Is he saying you can he's just saying in a way it is a construction of type, because you can draw infinite amounts of straight lines on top of other straight lines that are equal to each other, all of which would have to be equal to each other. So without saying you can draw them, you can. Or is that too simplistic?
Okay. That's
what I was getting from.
Okay, I'm going to give you a little sneak peek here into the next reading. Well, I'll just let you wait till you get there. It's proposition 11. It's going to be interesting in this regard. We should probably wrap up here. I'm sorry that I'm afraid that if you're going along with me on this journey, we're going to probably end up with more questions than answers. We'll get answers, but those always lead to more and harder questions. It's kind of the nature of the beast, I think. But I think these are good questions. At least this much seems to be clear in Euclid starting out. First, he's starting out, he says, I need to start out with things that are proper to geometry, but I also have to have these ideas which go beyond geometry. So both of those are going to be involved as starting points. Some things that seem to be starting points of maybe even certainly all kinds of thought, maybe all thought. Those have to be an element in this, if it's distinct from the definitions and postulates which are proper to this science. And then at least we'd see this. Do we think it's right that postulates 1, 2, and 3, if you compare them with the definitions that correspond to them, so to draw a straight line from any point to any point, compare that with the definition of straight line or definition of point, that's a constructive sort of thing. The definition isn't a constructive thing. It might not even be a statement exactly. Maybe it's just giving you the meaning of a word. But at least those first 3 postulates seem to be constructive as distinct from the definitions. So, all right, think about that. And we will see that it'll be interesting to see when we look at one of the propositions in a little bit. So in the next assignment, to be thinking about the right angles, particularly as we come up to them, he's going to be dealing with right angles in these postulates in the next assignment. So we're going to read propositions 5 to 17. And by read, I want you to at least look at all those propositions so that you have the enunciation and you can look at the diagram and get a sense of what he wants to do there. You don't have to necessarily read through every step or understand every step. And then I would like you to submit demonstrations of 5, 9, and 16, but do what you can. I don't, if it's going to take you, usually with this sort of thing, I don't really want the assignment to take you more than an hour and a half or so. So if it's eating up more of your time, don't worry about it. Submit what you can. All right. Thank you all. This is a great beginning.